Okay, now we're going to work on a problem, the induction on trees, that's got multiple variables. So first off, I've defined a new function called flat, and what flat does, it flattens a tree down into a list. So it takes a tree that might look like this, 4, 3, 5, 6, 9, and it squishes it down into a list, 3, 4, 6, 5, 9. So it flattens the tree down into a list. So how's flat defined? Flat's got two arguments, one for the tree and one for what's called an accumulator, or like a temporary variable that stores like the total so far. So flat null ACK returns the total. And for a tree with stuff in it, flat node A T1 T2 calls flat T1. So it takes the first tree here and calls it again. It takes the argument A and then cons that onto the front of flatten T2 with ACK. So we take, missing ACK here. There we go. I take my temporary variable ACK. I pass that to flatten T2 with ACK. Whatever the result of that is, that's going to be some list. I then cons A onto the front of that. And then this whole thing here is my new accumulator for the outside flat. So then I call flat T1 with this whole thing inserted for ACK. Right? You might have seen a different definition in 1100 using concatenation. So like flat tree is like flatten T1, concatenate A, concatenate flat T2. So you might have seen something like this. Flat node A T1 T2 is flat T1, concat A, concat flat T2. This definition is equivalent to this definition, but we're using this one because it's a little bit easier to do proofs over. This one gets a bit messy due to the concatenation, so we're going to use this definition here. And the property we'd like to show is for all trees T, for all lists ACK, if you flatten the tree with the accumulator and then take the length of it, take len of it. Oh, by the way, len is a function that computes the length of a list. I've called it len just for brevity's sake. You've seen this function before. So if I flatten a tree with some list ACK and then take the length of it, it's the same as the size of T plus the length of whatever the temporary variable is ACK. Okay, that's the property we'd like to show. I've got two variables here. So which one do we induct over? Well, if we look at the inside term, flat is sort of inducting over the tree. It's breaking up the tree, whereas the ACK variable is sort of basically passed on. So it looks like we should do induction over the tree, and given this is a tree induction question, to expect that to be the case. So we're going to prove by tree induction on T. Okay, so what's our base case? Our base case is when the tree is empty. So base case T is the null tree. So we want to prove for all lists ACK that the length, if you flatten the null tree with ACK, is the same as the size of the null tree plus the length of ACK. Okay, that's the thing we'd like to show. So we'll let ACK be an arbitrary list. And then we're going to start from the left-hand side and proceed. So the left-hand side is length of flatten the null tree and ACK. Let's look at the definition of flatten. If the tree is empty, which it is, this just returns ACK. This becomes len of ACK by rule F1. Okay, and now I've got to somehow get from here to the right-hand side. Well, we know the size of the null tree is empty, is 0, I beg your pardon, from definition. So what I can do is add in a 0 term here, and then use this rule backwards. So I'm going to write this as 0 plus len ACK by math, because anything plus 0 is 0. Anything plus 0 is unchanged. And then I can replace the 0 with size of the null tree, using S1 backwards. So we have size of null plus len ACK by S1. And this is equal to the right-hand side. Okay, cool. Base case is proven. Now we want to prove it for the step case. Okay, so for the step case, we're going to make two assumptions like we did before. And because we're trying to prove for all T, for all ACK, this property, when we assume it for a tree T1, we're going to be proving all of this statement here. So we want to prove, we're assuming for all ACK, len of flat T1 ACK equals size T1 plus len ACK. That's the inductive hypothesis first. And the second inductive hypothesis is exactly the same thing, but with T2 inserted for T. So we're going to assume for T equals T1 and T equals T2. And then we want to prove it for T is equal to node A, T1, T2 for all A. Okay, so proving that for any new arbitrary variable A. So that is, we're proving for all A, for all AC, len flat, this whole new tree we've constructed, AC, equals the size of the new tree we've constructed plus the length of AC. Okay, so we let A and AC be arbitrary, and we'll start from the left-hand side. So the left-hand side is all this, the length of flattening the new tree, node A, T1, T2, and I'll list AC. Okay, what is this equal to? Look at the definition of flat, so we've got to be careful here. Flat node A, T1, T2, AC. So we take the T1 out the front, and then AC is replaced with flatten T2 with AC, and then cons A onto the front. So this become length of, and we just follow the rule directly, flat T1, cons the A on the front, and then flat T2 AC. T2 AC. Okay, by F2. Alright, what can we do now? So we want to be able to somehow get this term back out. Well, thankfully I can use my inductive hypothesis here, and it's not immediately clear why, but let's look very carefully. So this is computing the length of flat T1 and some great big list. Whatever this thing is, it's definitely got to be a list, right? So if we look at our inductive hypothesis, we've assumed for any value of AC, I can replace this term here with these two terms here. So even though this isn't like literally AC, it's some list, and I've assumed this is true for any AC. So I can make this replacement here, and again I've got to be careful, so we'll look at the rule directly, take the tree out and compute size of T1, and then take the list out and compute the length of that list. So this is going to be the size of T1 plus the length of this whole list here. Len of A cons flat T2 AC. That's by the first inductive hypothesis. Okay. What can I do now? I want to get rid of this pesky A, and I can do that by the definition of length. I get len. Len of x cons xs is 1 plus len xs. You can take the x out the front, because the length of this whole list is 1 plus the length of xs, because x is just the first element on the list. So this is going to be size T1 plus, and then what's all this going to be? So it's going to be 1 plus the length of what's left over. Len flat T2 AC. By, what rule was that by? That was by the rule for length, L2. Okay? And now this term here looks like my second inductive hypothesis, so we can apply that. This is going to be size T1 plus 1 plus whatever this evaluates to, size T2 plus len AC. Size T2 plus len AC by rule inductive hypothesis 2. Notice how I'm leaving the brackets, I'm not changing the order of anything. And so now what I'm going to do is I'm going to change the order, because I know addition is associative and addition is commutative, so the order in which I evaluate these doesn't matter. So we'll go up to here. So this is going to become, what order do I want to put this in? Well, I want to put this in an order such that I can rearrange it to make all the size terms look like this. So if we look at the definition of size, I want to rearrange it so it looks like 1 plus size T1 plus size T2. So I can do that. 1 plus size T1 plus size T2 plus len AC by math. So all I've done is just rearrange the order of the terms. And now this term here I can use S2 backwards to obtain size of node any x T1, T2 plus len AC. So this will be, for any x, this property by S2 backwards. And if this is true for any x, then it's true for any particular thing I can choose, so I'm going to choose A. Size node A T1, T2 plus len ac. By math, if you want to be pedantic, I guess for all elimination, but you don't really have to say that. You can say by math or by logic, perhaps. Yeah, by logic this is true. And this whole thing is equal to the right-hand side. Okay, so that was a bit of a lengthy proof. It's a bit of a tricky one because you have to recognize you can apply the inductive hypothesis here. Even though this doesn't look like AC, this thing is a list, and we assume the inductive hypothesis for any value of AC. So that's why we can make this step from here to here. That's the tricky one. So we're proving it for the base case. We assumed it's true for two subtrees and proved it's for the bigger tree made out of those two trees. So it's true for the step case. Therefore, this statement here is true for any choice of tree T and for any choice of length of any choice of list AC. So we've proven the thing that we wanted to prove.